What specific problem does the OOD-CHAMELEON method aim to solve in the context of OOD generalization, and what are the key types of distribution shifts it addresses?
The OOD-CHAMELEON method aims to solve the problem of selecting the most suitable learning algorithm for out-of-distribution OOD generalization tasks, particularly when faced with complex real-world distribution shifts. It addresses the challenge of accurately predicting which algorithm will yield the most robust model for a new unseen dataset without relying on trial and error. The key types of distribution shifts that OOD-CHAMELEON focuses on include covariate shifts (CS), label shifts (LS), and spurious correlations (SC). By framing algorithm selection as a classification task and training on a diverse dataset of datasets that exemplify these shifts, OOD-CHAMELEON seeks to improve OOD generalization by learning the interactions between dataset characteristics and algorithm performance. This approach allows for better algorithm selection, tailored to the specific nature of the dataset at hand.
Can you explain how the proposed OOD-CHAMELEON method works? Please illustrate this step-by-step through the algorithm selection process, including details on the training of the algorithm selector and the construction of the meta-dataset.
The OOD-CHAMELEON method operates through a structured algorithm selection process aimed at improving out-of-distribution OOD generalization. First, it constructs a metadataset by generating a diverse collection of datasets that exhibit various types of distribution shifts, specifically covariate shifts, label shifts, and spurious correlations. This is achieved by sampling from synthetic distributions or real datasets, such as Celeba, and quantifying the degrees of these shifts to ensure a comprehensive representation. Next, the algorithm selector is trained on this metadataset, which consists of dataset descriptors, summarizing the distributional characteristics, paired with the performance metrics of candidate algorithms across the generated datasets. The training involves different formulations, including regression, multi-label classification, and pairwise preference learning, to predict the most suitable algorithm for a given dataset based on its descriptor. Finally, during the selection process for a new unseen dataset, the trained algorithm selector utilizes the dataset descriptor to predict the performance of all candidate algorithms, ultimately selecting the one that is expected to yield the best OOD accuracy. This systematic approach allows OOD-CHAMELEON to adaptively choose algorithms based on the specific characteristics of the dataset, leading to improved generalization performance.
Can you come up with a simple yet illustrative example demonstrating the inner workings of the OOD-CHAMELEON algorithm? Walk through the main algorithm steps with this example in mind.
To illustrate the inner workings of the OOD-CHAMELEON algorithm, consider a scenario where we have a dataset of images depicting cats and dogs, with varying degrees of covariate shift (CS), label shift (LS), and spurious correlations (SC). The first step involves constructing a dataset of datasets that exemplifies these shifts, where we generate multiple datasets with different combinations of CS, LS, and SC, such as a dataset with a high CS due to varying backgrounds and a low LS where the labels remain consistent. Next, we create a metadataset by training several candidate algorithms, like ERM and Group DRO, on each dataset and recording their performance metrics. The OOD-CHAMELEON algorithm selector is then trained on this metadataset, using dataset descriptors that summarize the characteristics of each dataset, such as the degree of shifts and data complexity. For a new unseen dataset, the selector predicts which algorithm will perform best based on the learned relationships between dataset characteristics and algorithm performance. Finally, the selected algorithm is applied to the unseen dataset, resulting in a robust model that effectively generalizes across the distribution shifts present in the data. This process demonstrates how OOD-CHAMELEON automates the selection of the most suitable learning algorithm, enhancing OOD generalization.
What are the theoretical or practical benefits of using the OOD-CHAMELEON method compared to traditional model selection approaches?
The OOD-CHAMELEON method offers significant theoretical and practical advantages over traditional model selection approaches. Firstly, It enables a priori prediction of the most suitable learning algorithm for a new unseen dataset, contrasting with traditional methods that require training multiple models and rely on restrictive heuristics. This approach is particularly beneficial in complex real-world scenarios where distribution shifts are multifaceted, as OOD-CHAMELEON is designed to handle various types of shifts, covariate, label, and spurious correlations simultaneously. Empirical results demonstrate that OOD-CHAMELEON consistently selects algorithms that yield lower test errors than any single candidate algorithm, showcasing its effectiveness in improving OOD generalization. Additionally, the method reveals important dataset characteristics that influence algorithm performance, enhancing our understanding of existing algorithms' applicability under diverse conditions.
How was the OOD-CHAMELEON method validated or tested? Please detail the experimental design, datasets used, and the performance metrics that were evaluated.
The OOD-CHAMELEON method was validated through a comprehensive experimental design involving both synthetic and real-world datasets. Initially, a metadataset was constructed from 7,392 synthetic datasets generated with varying degrees of covariate shift, label shift, and spurious correlation, which were then used to train the algorithm selector. The performance of the selected algorithms was evaluated using metrics such as 0-to-1 accuracy and worst group error on 2,000 unseen datasets with distinct properties. Additionally, the method was tested on real datasets derived from Celeba and Cocoa, where it demonstrated significantly lower worst group error and higher accuracy compared to baseline methods. The results indicated that the algorithm selector effectively adapts to the nature of the dataset, confirming its robustness and generalizability across different domains.
What specific results were achieved with the OOD-CHAMELEON method, and how do these results demonstrate improvements over existing algorithms?
The OOD-CHAMELEON method demonstrated significant improvements in out-of-distribution OOD generalization by consistently selecting algorithms that resulted in lower worst group error and higher 0-to-1 accuracy on unseen datasets compared to existing baselines. Specifically, the algorithm selectors outperformed random selection, global best, and naive descriptors, achieving a notable increase in accuracy and a decrease in error rates. The results indicated that the learned algorithm selectors generalized well across different datasets, including those from real images like Celeba and Cocoa, confirming the robustness of the dataset descriptors used. Additionally, the pairwise preference learning (PPL) formulation achieved the best performance, highlighting the effectiveness of using classification over regression for algorithm selection. Overall, these findings underscore the capability of OOD-CHAMELEON to adaptively select the most suitable algorithms based on dataset characteristics, thereby enhancing OOD generalization beyond traditional methods.